Hi, my name is Akram Helou. I am a SURE participant and a rising senior in computer science and engineering. My research project was supervised by Professor Satinder Singh, Richard Lewis, and graduate student Jonathan Sorg. Our research project investigates the properties of rewards in reinforcement learning, or RL for short. RL is an unsupervised learning problem and a sub-area of machine learning. We'll define a RL problem using a Markov decision process, or MDP. MDP is a tuple, where S is a state of states that an artificial agent can be in, A is a set of actions that an agent can take, and P of S and A defines the distribution of next states S prime that an agent can be in if it takes action A in state S. Gamma is the discount factor, and it defines the relative importance of recent and past states. R is the reward function, and basically it tells the agent how well it is doing. If the agent takes an action A in state S, it will get some scalar that tells us how well it is doing. We can trace what an agent is doing by looking at its trajectory. Suppose an agent starts in state S0, takes action A0, and then will get reward R0. It lands in state S1, takes action A1, and then gets reward R1, and so on and so forth. The goal of an agent is to maximize this expression, or the expected value of the discounted sum of reward. An agent behaving as such is said to be solving the problem optimally. We want to study the properties of the reward function in RL. RL researchers have long chosen to abstract away the problem of studying the source of such rewards to make rapid strides in solving the pure learning aspect of a RL problem. But in complex problems, reward functions can be too difficult to specify, and hence it is better if we can derive them. To underscore the importance of rewards, consider that the developmental psychology literature informs us that intrinsic motivational systems, guided by robust intrinsic rewards, impel animals and humans alike to engage in activities that are likely to give them the opportunity to learn useful skills for future use when trying to fulfill a specific external goal, like I want to get a PhD. Finally, specific reward forms allow us to design approximate algorithms that can find good action policies quickly. In our case, we study the properties of rewards using a general computational optimal reward framework, which searches over the space of rewards for the optimal reward that makes an agent act optimally according to some fitness measure. Let us clarify this using one of our simplest experiments because of time constraints. Consider a 6x6 grid roll, as you can see here, where there's a food source in the upper right-hand corner and a water source in the bottom right-hand corner. There's also a fitness function that measures how well the agent is doing in its lifetime. The fitness function gives an agent a positive scalar if it is not hungry and 0 in all other states. The higher the fitness, the better. But the agent can only eat from the food source once it drinks from the water source prior to that. The agent needs to learn all this autonomously. We want to find the reward that allows the agent to learn this behavior the fastest in 75,000 time steps. The reward function maps the agent's hunger status and thirst status to a scalar in the -1 to 1 range. So we search over 3,240 of these rewards. We find that the best reward has this form. And from the first graph, we see that it does significantly better than most other rewards. The second graph describes to us the characteristics of the best rewards. In short, the best reward will penalize the agent for being thirsty. This makes sense because an agent cannot learn to eat before it learns to drink. Thus, we see how the best reward exhibits an intrinsic motivation for drinking water, exactly what we need. Our research investigating the properties of reward is impactful for social and behavioral sciences because it paves the way for using RL as a scientific analysis tool. These sciences are usually interested in explaining behavior in complex systems, but they often neglect to find the evolutionary origins of such behaviors. For instance, The influential prospect theory explains how humans behave when faced with decisions that involve risk. It is especially important in economics. Very simply, it says that if someone is poor with respect to some measure, then she is willing to take increasing risks to get high payoffs. However, if someone is rich with respect to the same measure, then she is more likely to stick with low-risk decisions that lead to a medium payoff. But why this behavior occurs is not explained, even though an explanation would allow us to better understand human decision processes and possibly change their risk predilections. Our framework can simulate thousands of agents and put them in situations where they are faced with similar decisions as humans that involve risk. By finding the optimal reward, we can read off the classic prospect theory curve, the one that you see right here. Thus, the simulation would inform us of the evolutionary origin of such a behavior and thus better understand it. We are about to conclude this experiment and get results for it. So, our future work is to conclude that experiment and get results for it. We also want to show how rewards can make approximately correct algorithms that find approximate policy quickly. As a side project, I'm also working on the benefits and limits of sensory motor representations, and I'm also working on how to make the agent learn to control its own memory to solve a problem efficiently. And that is all. Thank you.